Okay, so let me go back and find that guy. All right. So that was the introduction to series, wasn't it? Yes. Right, what do you want me to do in that area? And in particular? What, just talk about 11 too? Or is there some specific you want me to go over?
Can you go through the general idea of 11-2?
Sure, okay. So what we're looking at is, what is a series? Well, a series is what you get when you add up all the terms in a sequence together. So if you imagine a sequence like 1, 1/2, 1/4, 1/8, forever. That is a sequence, right? It's an independent list of numbers that has some kind of pattern to them. And if you wanted to know what that particular one is, that's its general form. But in this particular case, it ends up being 1/2 to the n minus 1. Well, that's a sequence. They didn't spend a lot of time on sequences. In fact, we only spend one section on it, 11.1. What are more interested in is the series. And the series is a single number, typically if it converges, at least it will be, that you get by adding up every single term in a sequence together. And the idea behind this is that in some situations, but not all these things added together will, I shouldn't really say the word equal, but they will have a limit that's equal to something. In this particular one, we would say that its limit was 2. So if you kept on adding this forever, you would get an answer that was essentially homing in on 2, right? It wouldn't quite reach there, but theoretically, it would get to the point where you couldn't tell the difference. And a lot of the time we spent on the rest of chapter 11 was finding out if a particular series converged or not. So we introduced an idea like that, guy. Sometimes it starts at 2, it really doesn't matter. And that is a shorthand way of saying add up a whole load of terms. And we spent a lot of time trying to find out whether a particular series converged or not. And that generated an awful lot of different kinds of series. And for different kinds of series, there were very often a particular test that we would associate with it. So off the top of my head, for instance, we have one that's called a geometric series. And so these were series that came from a geometric sequence, and they would look maybe something like this. And if you write down what this one looks like, it would be 3 plus 3/4 plus 3/16 plus C/64 forever. And when you have a series that is basically made up of a whole load of things, in this case added, but the key factor is that each one to the next is 1/4 as big. Isn't that the idea between a geometric series is you multiply the next guy and, you know, forever. And for those kind of ones, didn't we have a test that was to do with the common ratio called R? In this particular question, what would the common ratio be?
Would it be 1/4?
It would be 1/4. And with the test, it says the absolute value of it. So the absolute value of 1/4 is obviously 1/4. But the test says if it is less than 1, doesn't the series converge? And if it is greater than 1, then it diverges. And you have to be aware that each test has that kind of bit at the end that says if this is true, it converges. And if that is true, then it diverges. for a geometric series, if you get that, you have a converging series. If you get that, you have a diverging series. That's pretty much every single geometric series in the world. You can tell whether it converges or diverges. Some tests have little holes where if this happens, you don't know if the series converges or diverges, right? In fact, a lot of tests have these little holes where you can't tell. Top of my head, the ratio test. See, if you do the ratio test, no, it's a different test, but if you do it and the answer ends up being 1, that is inconclusive, right? We don't know if it converges or diverges. In the ratio test, if the limit is less than 1, it converges. If it's greater than 1, it diverges. But if it's equal to 1, you don't know. The nth root test does that as well, doesn't it? So some tests have little gaps in them. And so we spent a lot of time, all of chapter 11 virtually, except maybe a bit towards the end when we dealt with series. We had a large number of tests, and I'll just do them as they come into my head. We have a geometric series test, and that one was basically, we've talked about that. So if the common ratio is less than 1, it converges. If it's greater than or equal to 1, it diverges. And for the geometric series, when they converge, we even have a formula that tells you what it adds up to. That's the A over 1 minus R guy. We have a thing called a P-series test. P-series test is for guys that look something like this. So sigma 1 over n cubed, sigma over 1 over n squared, 1 over n, 1 over the square root of n, right? Things like that. They are essentially P-series. You're allowed to have a number in the top like 10 over n squared as well. And in that case, I better move my numbers down. It's all about the power, the value of P. Can anyone remember what a P-series test, what value of P converges and what value of P makes it diverge? It's very specific.
Greater than 1 that converges?
Correct. And less than 1 or less than or equal to 1?
Less than equal to.
Yeah. So in the P-series, again, there is no hole, right? Again, there's no particular rhyme or reason. These are just as they come into my head. There's another test, which a lot of people make the mistake of trying to use it and get conclusions that aren't true. Essentially, what the divergence test says, if you have a generic series like that, if the limit as n tends to infinity is equal to a number, right? And that number L is not 0. So if it's a half, or 2, or -7, right? If it's not equal to 0, then the series diverges. And that's called the divergence test. What a lot of people mistakenly think is that if that limit is 0, that means the series converges. It does not mean that. Right? If the limit as n tends to infinity of the individual terms is 0, we say that the test is inconclusive. I'll give you an example of why that's true. If I use a P-series on you, here's 2 P-series. Isn't the limit as n tends to infinity of 1 over n 0? Isn't the limit of 1 over n squared also 0, right? Doesn't this one converge and that one diverge? So you see that the divergence test only tells you when things diverge. When it's inconclusive, because the limit is 0, either of those two could have, right? It might converge, it might diverge. You don't really know. You have to find one of the other 9 tests to figure that out. Now, I could actually keep going with this. I'm not quite sure how much of this you want me. You want me to keep going? Okay. So that would be one of our many tests that we've done. Now, it would be really great if we only needed 3 tests, wouldn't it? I mean, we could do this in 2 weeks, not 5. But that's not the way it worked out. And what we ended up having to do is we had to deal with other situations, other series that didn't work with these, right? Divergence test didn't help us. It wasn't one of these and it didn't look like one of them. So, you know, what did we do? Well, one of the tests we have is called the integral test. And imagine we have a series. Instead of calling it A of n, I'm going to call it f of n. But I want you to think of a and n and f of n are just the same thing, just a different way right now. So if it's 1 over n squared, right, it just means, you know, 1 over n squared. Now, in the integral test, we have to show quite a few things. First thing you have to use the integral test is all the individual terms positive, right? You can't have negatives. Shouldn't this be decreasing, right? And the third one, hence the name, shouldn't the integral from 1 to infinity of, well, you can use it n or x, every letter you like, that guy. I actually tend to use x, I guess, because of my habit. Doesn't that have to converge to a number? Now, if all 3 things are true, is it positive? Is it decreasing? And is the limit from 1, is the integral from 1 to infinity, does it have a limit? Does it have a value? If all 3 things are 2, then the series converges.
What if the third condition diverge?
Then it diverges. But the first 2, that's this thing and this thing, must be true before you can even do the integral test. So don't jump into that and think that tells me the answer. Because I could create an integral where this exists, but the function went down the way and up the way and down the way and up the way. So the area might be a finite number, but the series, you know, was infinite, right? It didn't converge. So a lot of people forget that one. You could put, typically, can't you do that one just by eyeballing it? You know, 4n over n squared plus 1 is clearly positive. But what do you need to do in step 2? Because that does involve work.
The derivative.
Right, so you have to find the derivative. And what do you need to prove about the derivative to show it's decreasing? Right. And aren't you allowed a little bit of wiggle room? It doesn't need to be negative all the time, but doesn't it, you know, after 4 have to be negative? Because sometimes the first couple of terms, you know, don't behave. But when n is bigger than 4, everything's negative is all you need. And when you're doing this part, don't you have to bring a piece of calc 2 into play, which means you have to do the limit as t tends to infinity of 1 over t f of x dx. Can you remember the method that you use to find the integral from 1 to infinity involves doing this process? Now, if the answer is 42, converges. If the answer is infinite, it's, you know, diverge. If the answer is the limit doesn't exist, it still diverges, right? Because the limit doesn't exist. What does that tell me? Well, it tells me the series doesn't go anywhere, right? It might bounce around between 2 numbers, but it never levels off, which is bad news for a series because it can't converge if it doesn't have one value it's trying to become. Okay. You still want me to keep doing with this thing, or you got some other questions?
What about
Okay.
the geometric series?
We did the geometric series.
Not geometric series, harmonic theorem, sorry.
But harmonic is interesting. The harmonic series is really just a special case of the P series. This is what the harmonic series looks like. If you write it down, it's 1 plus a half plus a third, whatever. And that's just a special case, isn't that? P series, P equals 1, so it diverges. Okay. Anybody want to tell me what the next test is likely to be? I know what one I'm going to pick, but if you pick a different one, I might jump around. But what would be after the integral test, would you suspect?
Ratio?
That does come, but there's something before that.
Is it the limit comparison test?
Yes. It's not what I was going to do, Caitlin, but actually that is the next one. So I got them in order. So there are two very similar sounding tests. Just like Caitlin said, there's a limit comparison test. And might as well do the other one at the same time. And then we have the one that's just called the comparison test. Before we get into the nitty-gritty of what does the limit comparison test do, or how do you do it, and how do you do the comparison test, let's talk about when you should use it. You should only use a comparison test when there's something weird involved. Weird would be if you wanted to do a test on that kind of series, right? So if you see a sine, a cosine, an inverse tan, an e to the 1 over n, you know, weird stuff. Don't know how else to describe it, right? Non-polynomial stuff. Then you are very likely going to be using a comparison test. If you have one that looks like a normal fraction function, what I mean by that is there's no square roots in it. It's like n squared over 2n squared plus 1, right? Those kind of guys, where there's some kind of polynomial on the top, and there's some other polynomial on the bottom, right? Guys that look like that. Those are the guys that you would use the limit comparison test on, right? Okay. You would also use it if you had things like 2 to the n plus 3 to the n over 7 to the n. So things that look like geometric series, but a little bit wonky, right? A fraction, you know, you wouldn't normally get 2, wouldn't you only just get 1? Let's cover that one up. Wouldn't you normally just get 1 in a geometric series, right? A 3 to the n over 7 to the n, right? But if you've got 2 guys added or subtracted, then I would be looking at the limit comparison test. Or if you got a polynomial, you would look at that. Use the comparison test if there's square roots, if there's tans, you know, weird stuff, right? Non-polynomial, non-power, right? Now, for each one of those tests, there is a different, quite different method for doing it. So let's look at the limit comparison test. Right, now in the limit comparison test, what you do is you find, try to think of another word, you find another series to compare it against. Hence the name limit comparison. And so if I take just the individual term, we do a little bit of surgery on it, which essentially is you reduce this to its essence. You know, what does it really behave like? You know, when n is huge, won't that plus 1 not matter? And won't that plus n not really matter, right? 1 trillion to the power of 4 is so massively big. Do you think adding another trillion is going to make any difference, right? It's a bit like the American debt is so big. Do you think adding another million to it is going to make any difference? Nah, right? Comparison. So what you do is you take only the largest power, top and bottom, and then you simplify it down. And you can use either of these two because they both count, right? I can't remember. I sometimes jump between one and the other. I think normally, don't I normally just pick the 1 over version? But it doesn't matter. Both work. Now, what that guy is, he is your comparison guy. He's the guy that you're going to call BN. This guy here is the guy you're going to call AN, because he's from the original question, right? Your original question was, does this converge or not, right? Now, if I can then show that the limit of AN over BN, as n tends to infinity, the limit of AN over BN is equal to a number. And as long as that number is not 0 or infinity, right? If I can prove that that is a number, then the limit comparison test says that my series behaves the same way that this one would do. Now, that's not just a single term. You know, that is essentially, that's the series it's representing. Does sigma 1 over n squared converge? Yeah. Isn't it a p series p equals 2? So you normally are going to do a comparison test with a p series if it looks like this. And if you do a comparison test with this, a limit comparison test with these guys, isn't it going to be with a geometric series? Now, if you were going to do this one, the easy way to do the surgery is pick the biggest one on top and ignore the smaller choice. So 3 to the n will beat 2 to the n. So this one's going to behave, well, essentially, isn't it going to behave like a geometric series R is 3/7? And I know that's going to converge. And then we move on to doing this. So back to this question, we will find the limit as n tends to infinity. I'll actually start up here. We're going to find the limit as n tends to infinity of AN divided by BN. And AN is all this. So it's 2n squared plus 1 over n to the 4 plus space n plus n divided by bn, right? So that's an and that's bn. And since you almost always get fractions here, isn't there a kind of shortcut where you write the first one and then you just turn the other one upside down? So rather than trying to divide by a really messy 1 over n squared, can't we just multiply by n squared over 1? And then
Are you fine if we skip that first line?
I don't mind that.
Okay.
Yeah, I wouldn't mind. I just normally put that in for, you know, when you want to look at it. What I would do here is distribute. So n to the 4 plus n squared over n to the 4 plus n. Now, remember, the goal here is to hope that this is a number. I don't care if it's 42. I don't care if it's minus 70. I just want it to be a number. As long as I'm good with that, I know I've got an answer. You know, in this case, isn't it going to converge? We already know from here. At this point, you can do limits one of 2 major ways. Couldn't you do L'Hopital till you get bored? Eventually, you would get the right answer. Or you could divide top and bottom by n to the 4, which I kind of prefer in a polynomial world. Would you agree? In a polynomial, it's just less work. So it now becomes the limit is n tends to infinity of 2 plus 1 over n squared and 1 over 1 over n cubed. But then when you do brute force, you basically get 2 over 1. No, you get 2. So, yep, I got a number. Therefore, my conclusion is that the original series in this question converges. Now, suppose I compared it, a different question, but suppose the comparison was 1 over n, right? Can you imagine that was the comparison? Then isn't 1 over n going to diverge? And I do all this and I get a limit of 2. My conclusion will now be the series diverges. So do you see that this test, it depends on who this guy is, right? If this guy's a converger, so will this one converge. If this comparison guy, right, diverges, won't this diverge? So you might say, why do I need to do all this stuff in the middle? If you do not get a limit that's a number, right, 1, 2, a half, If you don't get a limit, it means you've screwed up over here. And therefore, I could pretend that that was the same as 1 over n, right? Can I just say, I'm comparing it to 1 over n. Well, if I did compare it to 1 over n, can you trust me that this answer here would be 0 or infinity? Which means you got it wrong. Try it again. You can only compare it to somebody he behaves like. You can't just say, I'll try and see if it behaves like, 1 over n cubed because I like 1 over n cubed today, right? You can't just randomly pick something. Now, that involves an awful lot of work, right? Because you've got to do the identification process. You're then going to do all this limit stuff, whatever way it works. Then you have to do, not have to do, but then the next one would be the comparison test. What you have to do here is for a different looking kind of series. So something weird is going to be happening, like that. Now, in this case, I have to know or kind of have an idea what this thing behaves like in its essence. Would you agree that sine squared n just kind of bounces between 0 and 1? Right? It won't get any bigger than 1. It won't get any less than 1. So my brain is saying, well, what's the worst case scenario? Always look for the worst case scenario, right? 1 over n squared. So I'm going to say, you behave similar to 1 over n squared. And then I'm going to try and set up a comparison like this. Is my original less than or equal to 1 over n squared? Is that true? Well, the bottom's the same, right? Would you agree that sine squared is always less than or equal to 1? This is true. So, conclusion, if you are smaller, which you are, than something that converges, what would logic say? If you're made up of things that are smaller than a series that converges, wouldn't logic be that you converge? And that's essentially what the comparison test does. Now, you can do the other way, right? You can make it go totally the other way. Suppose I had e to the 1 over n over n. Now, that's a weird one. E to the 1 over n, as n gets bigger, doesn't that become like a number almost e to the 0? But isn't it always at least going to be 1? And it's probably going to be bigger than 1, right? So based on that logic, won't this guy be bigger than 1 over n? Now, this diverges. We know that, right? That's sigma 1 over n. If you are bigger than someone that diverges, right, so you're larger, isn't the conclusion then that you have to diverge? So the comparison test is not as formal, in lots of steps and things that you do. Isn't it a little bit more rough and ready, right? You've got a series that's kind of weird looking, but you can find somebody that converges and it's smaller than that guy, or you can find a series that's bigger than him, and it's bigger, in which case it diverges. But what you have to do is make sure that it's true, right? So if I put a 2 here, to keep things happy, wouldn't I have to do that? And then couldn't I split this and call it a half of 1 over n? Well, isn't 1 over n going to diverge? Making it half of infinity doesn't help it. It's still going to diverge. So you may have to tweak it. Sometimes you put a 2 in the bottom, sometimes you put a 2 on the top. You have to make it work a little bit for you. Are we good?
So do you always have to make it like the same denominator then?
In the ones that you're likely to see, yes. Don't play about with the denominator if it's simple, right? Now, if the denominator did this to you, right? Something like that. I know that guy's going to behave like 1 over n. Agreed? I know that 1 over n diverges, so I have to show that this is bigger than a version of 1 over n. Now, it gets a little bit weird here. If you make a number on the bottom bigger, doesn't the fraction become smaller? So why don't I just stick a 2 on that, and that would be true. And then I can say it's a half of 1 over n, so it diverges. You see, you have to tweak it a little bit because, you know, sometimes it's n, you know, you have to tweak it, right? But if you can see it, aren't comparison tests literally 2 or 3 lines? There's not an awful lot of algebra in them. It's all about coming up with who does he behave like? In essence, who does he behave like? Normally, one of the easiest ways to tell is ignore the ugly guy and pretend it's 1. So I know that's going to behave like 1 over n, right? I know that guy's going to behave like a 1 over n squared. And then I might have to tweak it and call it 2 over n squared or 1 over 2n squared, you know, to make it mathematically correct. But once I know the essence, I'm good. Any questions so far?
I have one on telescoping series.
Why don't we do them next time, right? Is that a specific question or do you want me to just go over them?
Yeah, I was doing the one of the practice exams and I got a different answer than what was on there. Can we go over that one?
Well, I have been known to make mistakes. Jessica, do you know what the question is? And I'll just do it right now.
Yeah, is the sum from n equals 1 to infinity of 4 over n times n plus 2.
That guy. Okay.
Yeah.
So we call these series telescoping series. I guess I could call this a telescoping series test, but yeah, I guess I could. It is a test. It's a way. Some telescoping series converge, right, and others don't. Typically, when you get a fraction like this, it's going to converge. But one of the things that you tend to get when you have a telescoping series is not only do you know it's going to converge, you very often, as a bonus, you find out what it converges to, right, what it would add up to. So first thing you do is you break this guy apart, and it's called partial fractions. You remember that guy? Partial fractions. Now, there are a number of different ways you would have learnt this technique in Calc 2 when you were trying to integrate fractions that looked like, you know, this. I showed you the cover-up method, didn't I? Can't remember it? Here goes. I need to know, I need to know what number goes here, right? I want to find out who A is. So you cover up the n here, and then you plug 0 into what's left, and 4 over that gets me 2. That's how I find a guy. Cover up the n and replace what's left by the value that makes that 0. In this case, n equals 0 makes it 0. 4 over 0 plus 2, 4 over 2 gets me 2. Right, let's do this one. I want to know what number goes here, B. Cover up n plus 2. What value of n makes n plus 2 0?
-2.
And you plug in that into what's left, and 4 over -2 gets you -2. One of the things I can tell you right now about telescoping series is, don't you always get the same number, take away the same number, right? So if this guy's 5, I guarantee this is going to be 5, take away 5, right? It's just the way it's going to work out. Now, once I know this, what you do is you basically take your telescoping series, that's this guy here, and rewrite it in terms of its 2 partial fractions. And then you just plug in as many terms as you feel, but typically you find Sn. So you plug in 1, you get that guy. When you plug in 2, you get that guy. when you plug in 3, you get that guy. When you plug in 4, oops, you get that guy. And then you keep going, and at the end, you would get 2 over n, take away 2 over n at 2. Right? So can you imagine we're just basically writing down what you would get if you did n terms using n equals 1, n equals 2, and so on. Now, what should happen in a telescoping series is almost everything gets killed off by something else. So if you look at this -2/4, doesn't it get killed off by that one? If you look at this -2/3, doesn't it get killed off with this one? If I did another term, can you trust me that that -2/5 would get killed off later on by something here? And that -2/6 would get killed off by something here. So all that we have got left alive here is 2 terms, 2 over 1 plus 2 over 2. All the terms in the middle will get killed off. But if 2 terms make it alive at the front, aren't there going to be 2 guys left at the end as well? And you can actually use patterns. If the first one survives in each of these, won't the last one survive in each of these 2? So this last one would be that guy. Oops, there's a little minus in here. Now it's a little bit messy, but you have to figure out if this is this term, what would the term just before it look like? Well, instead of 2 over n plus 1, 2, wouldn't you have 2 over n plus 1? Instead of 2 over n, wouldn't you have 2 over n minus 1? And there's the second guy. So all these terms kill each other off except 2 terms in the beginning and 2 terms in the end. So can you trust me that one would eventually get killed off as well? And then you just say to yourself, what will happen to the partial sum if you made it infinite? Which is basically, what would you get if you added it all up? Well, you get 2 plus 1, take away 2 over infinity, take away 2 over infinity. Don't you get 3? Because 2 over infinity is 0. And if, as it is in this case, the answer is a number, can't you say this particular series converges to 3? Now, in other situations, probably not this one, but in other ones, when you do the terms, can you imagine I did a different story and it looked like this? 2 add 1, take away n plus 1, right? Something like that happens. Can you imagine a different series and we got that? Then wouldn't the answer here be it diverges? So telescoping series have the nice feature that if you break them down into individual fractions and then you do this trick here, that all the terms in the middle disappear except 1 or 2 at the beginning and obviously compensating 1 or 2 at the end. I don't know, is that the same answer you got, or did I tell you the wrong answer in my solutions? Because I have been known to do that.
No, the 3 was the right answer. I think it was just written wrong in the notes, but that's okay. I just want to make sure I'm missing anything.
Right, well, better to be safe than sorry. I don't know what number we're up to. Who cares? Let's call it 7. I think it's probably 7. We're running short of tests, aren't we? God, we're running short of time. We're running short of tests. Can anybody tell me either of the 2 that are left? I think we've covered all the others. Oh God, no, there are 3 left. I did miss one.
That the alternating
Yes.
series test, the ratio and the root one, right?
That's it. So let's do the alternating series test, because the ratio test and the nth root test are the last 2 that you typically would do. If that isn't the ratio test, the guy that you get lots of practice on because of the series stuff. So alternating series test. they look like this. Or they look like this. Or they look like this. I don't know, doesn't Web assign like the n-1 rather than n+1, but it's cosmetic. The thing that makes them alternating series is this thing here. Because when you plug this in, don't you get first guy, take away second guy, add the third guy, take away the fourth guy, add the fifth guy, take away the sixth guy, right? You get an alternating plus to minus. And the alternating series test says the following. Forget about the -1 bit. The bit that comes after. So for instance, if I did that guy, right? As an example. En, in this case, would be 1 over n cubed. And there's certain hurdles you need to show are true, right? Before you can actually do the test. People jump right into the last bit and they forget the builder. Doesn't the series En have to be decreasing? Doesn't it have to be positive? And lastly, doesn't its limit have to be 0? And if that is the case, it converges. And what happens if this is true and this is true, but the limit as n tends to the limit as n tends to infinity of an is a number that's not 0, right? Like the limit is 1 or 41, right? What happens, or what's the conclusion that you make if the last piece of the puzzle is a number? If the limit is 0, it converges. What happens if the limit is not 0? It's some other number.
Inconclusive.
No, it's better than that.
Does it diverge?
Yes, it does. So the alternating series doesn't have a hole in it, provided these two things are true. If this isn't true or that isn't true, you can't use the alternating series test. So I guess in that sense, it's inconclusive because you don't know, right? Because you can't use it, right? It only works if the series is decreasing and all the individual terms are positive. So if I was doing this one, would you agree that 1 over n cubed is obviously positive? There's nothing to prove, right? If n is 1, 2, 3 is positive. If I call my function f of n equals 1 over n cubed, can we do the derivative and can I tell you that the answer would be 1 over 3 times n to the 4? And it's not hard to prove that that is negative, isn't it? And then all you need to do is find the limit. Well, the limit as n tends to infinity of 1 over n cubed. It's hardly worth talking about because isn't it just brute force? Now, if that would be the baby one, I mean, if someone was trying to give you one that actually had some meat on it, wouldn't they be giving you things like, you know, something like that, right? Where you'd have to work at it a little bit, right? Anybody have a guess at that? Do you think that's going to converge or diverge? Because it passes the first two, right? It's positive and it's decreasing.
Converge?
Yes. I guess, or did you have a gut feeling for why it might?
Well, it's telling me that it is a comparison test. Oh, limit comparison test. My bad.
Well, yeah, but the -1 to the end stops the limit comparison test from working.
Well, after the first two category done, and then the third, we just do the limit comparison test, right?
No, you cannot use a limit comparison test on alternating series, because the limit comparison test has to always be bigger or less. If half the time your answer's negative, isn't it half the time going to be bigger and half the time it's going to be less? There's nothing fixed to compare it with. So we always do it with positive things. So if you ever see a negative one to the end, shouldn't you be thinking alternating series test or ratio test? Right? If you ever see something like that, that would be my most likely test. How I do these, if you cover that guy up, do you see he behaves like a 1 over n? I know alternating series 1 over n is going to go 0 on me, right? So it's going to converge. That's an alternating series test. What test would you use on that guy that looks very similar?
Comparison,
I would. What would you compare it to?
1 over n.
So it diverges, which it does. What other tests could you use, but you never should?
Integral test.
And why? Correct?
It's a mess.
It's a mess. Nobody wants to do the integral test. Would you agree? They're awkward, they're long, there's a lot of stuff going on. And, you know, if you did an integral test on that, trust me, one of the things you'd have to do would be a U-sub. Apart from the fact you still have to differentiate it. If you're going to differentiate it, isn't it going to be a quotient rule? Can you just see how long that would take? So avoid the integral test unless nothing else is working. Now, if it's an alternating series and it converges, let's do this one back here. Right. We've already shown or proved that that converges, right? If you use S5, remember S5 means you plug in 1, 2, 3, 4, 5. So let's see, it's -1 over 1 cubed plus 1 over 2 cubed, take away 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed. No, one of them's a minus. I am going to pretend I know the answer. It's not this, but just for argument's sake, we'll pretend it was, right? Because it's an alternating series, can't we also put a prediction on what the error is going to be? In other words, if I use this to estimate the whole thing, isn't there a thing that says the error is plus or minus the next number, the one you didn't use? So if you stop at 5, isn't A6? Now, in my particular case, won't A6 be 1 over 6 cubed? And 1 over 6 cubed is actually pretty small. So 1 divided by 6 cubed is roughly 0.005. So wouldn't I be able to say plus or minus 0.005, which would be what? Good to 2 decimal places. So an alternating series allows you to predict what the sum will be if it converges. Telescoping series does the same job, right? Part of proving it converges is to actually find what it converges to, right? So you actually get it as an extra benefit. Any questions before we go for the last 2 then?
Will there be error formulas in the test?
Well, you write them down if you want to use them. I'm not going to tell you. Your job. If you already know that, I guess you didn't need to. If you're saying, I don't remember that, you probably should write it down.
Like, will it specify though if it wants us to do the plus or minus, or should we just add that on?
You will assume that is, you know, if I say what's the error, won't it be something plus or minus something?
Oh, gotcha. Yeah. Okay, thanks.
I would ask if I wanted to, I would say, there are 2 versions of that question. One is, you're using S5, what's your error? Which would be this, right? Isn't the other question, how many terms do I need to get 5 decimal places? You remember those ones? How many terms do I need to get 5 decimal places? So what you do is you go, right, an plus 1. You could do an, it works both ways. An which is 1 over n cubed. For 5 decimal places, you actually do that guy. And you notice that there's 5 zeros and a 5 for 5 decimal places. You then solve that. And if Desmos is around and you choose the right window, can we pretend this is 5.316, just for argument's sake? How many terms will you need to get the accuracy that you were looking for? 5 or 6?
6.
6. Always round up. So even if it's 19.002, you'll still make it 20, right? To be sure, to be precise. Okay, ratio test. What number am I up to? 8. Yeah. Now, there are some features that kind of tell you you're probably going to be doing a ratio test, but here are some of the things that ratio tests have. Oh, and you don't need a fraction for a ratio test. Could that also be a ratio test? What is the giveaway that a ratio test is going to be used in at least 3 of these questions?
Is it the factorial?
Yeah. If you see a factorial, don't even think of anything else, right? It's a ratio test. End of story. It's a ratio test, right? Now, that one does not have a factorial in it, yet it is still a ratio test. That's a little bit more subtle. Why do I know it's a ratio test and not, I don't know, a limit comparison test or whatever? What's it got that stops that from being the test? Why?
The numerator is not technically matched with the denominator because the 2n in the n plus n to the power of 3 is not sharing the same border.
Right. So if you see powers and polynomials, then you're pretty much sure you're going to do a ratio test. Right. Now, if they were all powers, couldn't we use one of the other tests? And probably should. If they were all, those kind of guys, shouldn't we also use one of the other tests, either comparison or limit comparison, right? But yeah, when you see powers and squares and cubes and 2 to the n's and 5 to the n's, that's a ratio test. You see the difference in look. And it doesn't matter if they stick a -1 to the n on it, it's still going to be a ratio test, right? So if I stuck a -1 to the n on any of these, that one's come over, but any of the others, wouldn't it still be a ratio test? So don't think, oh, well, because I see this, it must be an alternating series test. If you think about it, can you really imagine trying to differentiate that? I mean, for practical purposes, would you agree that would be horrendous? So that's another clue that it's not the right way. So ratio test it is. So in the ratio test, you basically find the limit of the absolute value of an plus 1 over an. And an are these guys. There's 4 to pick from. They're not the ratio test, so don't pick those. Which one do you want me to do just as an example, working it through?
You do 3 to the n factorial.
Okay, so is going to be the limit as n tends to infinity of the absolute value of 3 to the n plus 1, n plus 1 factorial over 3 to the n over n factorial. Now, factorials do play well together. But let's take care of these guys. Would you agree that 3 to the n plus 1 cancels out the 3 to the n? So what's left, and is it on the top or is it on the bottom?
Three on the top.
3 on the top. Now, n plus 1 factorial and n factorial, they cancel as well. And hopefully you've done enough of those to realize that there's n plus 1. That's all that's left, n plus 1. In this particular case, would you agree it's also on the top? I guess if you want a fraction, you can do that. I don't want one now. In this case, can't you just brute force it? In which case, the answer is infinity. And if the answer is anything bigger than 1, right, it diverges. So if the limit is equal to L, right, and L is anything bigger than 1, you are looking at a diverging series. If L was a number and that number was, less than 1, then it converges. And if the number is equal to 1, they have inconclusive, right? So I don't know, depends on what the thing is. If it's inconclusive, maybe you could try one of the other 8 tests, right? You may get better luck with that one. Let's do this horrible one that's got all the pieces to it as the second one then. When we did the limit comparison test, we have very similar algebra, didn't we? Have an over bn, and both of them are fractions. And so I did a little shortcut, which I'm going to try and do here as well. If you take this guy and make everybody n plus 1, you get that guy. 2 to the n becomes 2n plus 1. N factorial becomes n plus 1 factorial. And n squared becomes n plus 1 squared. And then an is basically this guy on the bottom. But if you turn them upside down, you can save yourself one line of working. Now, I'm going to cancel out all negative ones. And because something is in an absolute value, won't that destroy the sign? So it's basically anything negative 1 goes. So technically speaking, is it a negative 1 left on the top, but the absolute value of it destroys it, it's back to 1. Okay, anything in the top, anything in the bottom that you can see that cancels. And tell me where it goes when it's finished.
There's a 2 on the top.
Great. Got some more cancelling.
There's an n plus 1 on the bottom.
And I typically leave these 2 guys alone for a little while, right? Because really it's probably a good idea to do a bit more work on those. So right now I'm doing the limit as n tends to infinity, and I've got 2 over n plus 1, and I've got an n squared over an n squared plus a 2n plus 1. Essentially what I did there is I filed that out. So far so good. I've taken the absolute value away here because we made everybody positive, right? So absolute value of a positive thing is still positive. Couple of ways to do this one. Anybody got any ideas how you would finish it?
L'Hopital on the n squared over n squared.
Okay, so if you want to do that, which is totally fine, what you need to do is separate it into 2 things and find the two things on their own, right? And if I picked you up right, you're going to do L'Hopital. Can I trust can you trust that that's going to be 1? Can you see it's going to be 1, right? Now, this is allowed. See if you've got the limit as n tends to infinity of somebody times somebody else. You sometimes find it easier to split them into 2 separate limits. You can see the math is a little bit easier to deal with. Now, we're talking about this guy. The answer is 1. What's this guy going to be when n goes infinite?
N to infinite, that would be 2 over infinity, which is 0.
And so the whole answer is 0. And as long as you are a number, and 0 is a number, right, that's less than 1, which you are, doesn't that mean that this series converges? And that would be your conclusion. There are no easy to look at expressions for finding out what a sum that converges that you've used the ratio test. You might see some formulas for it, but it's not a biggie. Normally, we're happy that you can prove to me that it converges or diverges. Unfortunately, in a lot of homework questions, in fact, some of the online test questions, you only had 2 boxes. One said converge and the other says diverge. And you had a 50-50 chance of being lucky. If I don't see all the proof stuff, and all you tell me is that it converges, and you say, but it's obvious that it converges because this guy is obviously bigger than that guy, and therefore every other question I've done, this was true, it's still going to get you 0 points, because I'm not, in a way, even that interested. Is it converging or diverging? What I want to know is, can you prove it to me? Can you use one of the 9 tests and prove mathematically that it converges? We've been in mathematics proved numerous times that what we thought was intuitively obvious ended up being wrong, right? We've always thought, well, x squared can't be -1. That's intuitively obvious, until someone said, well, that's because your number system wasn't any good. Your number system should have been the complex number system, and now it works, right? Do you know the Greeks believed that you couldn't get square roots? Square root of 2, they didn't even have a name for it, because the concept that anything couldn't be a fraction was stupid to them. Yet the square root of 2 is not a fraction. Right? So you can't look at that and say, well, I can tell because I've done enough of these that this is going to converge or it's going to diverge, because I bet you there's a series out there that someone could create that your intuition would say go one way, and the answer is actually the total opposite, right? So you can't build bridges by saying, oh, it looks like it's 150 feet, because the last 5 bridges I built, I was really good at judging the distance. Right? Not a good attitude. So prove it. Oh, we still have one last guy in the list. God, that's a lot of names. It's called the root test. I think it's number 9 we're up to. I prefer another name, because I think it helps. It's called the nth root test. Now you use those guys when you have to do things like that. The thing that makes these guys the root test isn't it these funny powers, like to the power of n squared or to the power of -2n. Technically, that would be 1 over n to the power of n, right? That's what makes these a root test. There are no factorials. If you see a factorial, it's a ratio test, right? End of story. ratio test. But if you see this kind of thing going on, right, we are going to be looking at the nth root test. And right, so let's show you what that says. It says for any series, if you find the limit as n tends to infinity of the nth root of that series, and it's equal to a number. If that number is less than 1, the series converges, just like the ratio test. If that number is bigger than 1, the series diverges, just like it does in the ratio test. And if it's equal to 1, it's inconclusive. Okay, so take each one of these and show you what it would look like. Right, if I'm doing this one, because that's probably the easiest to do. The limit is n tends to infinity of 1 plus 3 over n to negative 2 over n. And I want to find the nth root of it, right? As long as you're good on the algebra of what that means, you'll be fine. Doesn't that guy kill off this fella? And you're now left with that. Great. I'm going to change this question. Otherwise, I was about to get an inconclusive, and I didn't want an inconclusive. I mean, it would be a good question. The answer would just be it's inconclusive. Now, in this case here, you can just do brute force. And that is definitely less than 1, so this converges. Great. Let's do this one. That's this guy. And we take the nth root of it. Okay. What does this expression become if you take the nth root of it?
Over n.
And if you brute force this, don't you get 0, which is definitely less than 1, so it converges again, right? I'll keep the best till last. And I change that just to n squared. Make it, a reasonable question to do. So we want n plus 1 over n to the power of n squared, right? And we want to take the nth root of it. Okay. What does this expression here become when you take the nth root of it? How do the nth root and the n square power interact?
They would subtract each other, right?
So what would I write down?
N plus 1 over n. Wait, is that n square? Or it's just n?
That's n squared here. So what do I write down here? Oh, this is n squared, sorry. Let's make it n. Yeah, I like n.
And with the power of n.
Agreed. Basically, just divide that by n, right? N, 1, negative 2, right? Now, this guy involves us doing a piece of magic. And rewriting it like that. And I told you, I know I did, a piece of magic where I said, if you ever see that situation, 1 plus a number over n raised to the power of bn, it's equal to something. Can
That's
anybody
e to the
do-
ab, right?
E to the AB. So in this case, would you agree A is 1 and B is 1? So this would be e to the power of 1, which is e. Isn't e greater than 1? So this one diverges.
Now,
Are we-
when writing this down, what do we say? Conclusion diverges by root test.
Nth root test, or that converges by ratio test, or converges by insert name of test here.
All right.
So when you come to a conclusion at the end, whether it's a converge or a diverge, hopefully you won't get an inconclusive, but even if you did, you would still finish with by insert name of test here.
And on the ratio test, isn't there
Mhm.
some of them that we will need to well, when we're trying to find the interval of convergence?
Okay, that's that. Yeah, that is the ratio test being used for another job. It's still, we're talking right now only about the tests when there's no x's involved, right? Everything's
Alright.
just n's, right? And when you start introducing power series, then the ratio test is your go-to guy, because isn't he the guy that gives you the ratio? The ratio test gives you the interval and the radius of convergence if you do it properly.
All right.
There are two kinds of convergence in the world. One is called absolutely convergent and the other is called conditionally convergent. You typically get these questions when the series has a -1 to the n in it, right? It's got some kind of alternating thing going on. And so essentially, it says the following. If you have a series that converges and when you make everybody positive, it still converges, then you say that the series is absolutely convergent. An example of a series that does that might be -1 to the n over n to the 4. That converges, prove that by an alternating series test. If you made everybody positive, which is what that is, don't you get 1 over n to the 4? But isn't that also going to converge as a p-series? So we call series that do this absolutely convergent. If you have a series that converges, and then you make everybody positive, so you get rid of the -1 to the n, essentially. And when you do that, the new series diverges. Then in that case, we call this series conditionally convergent. If you want to see what an example of that would look like, how about -1 to the n over n? I can prove that that converges using the alternating series test. If I make everybody positive, doesn't he now turn into that guy? And isn't that a harmonic series, a p-series, and it diverges? So this fella is conditionally convergent. This fella is absolutely convergent. Now, that doesn't change one iota every test that we've done, right? They'll still do what they do, and that's fine. But you may get a question along the lines of, is this series absolutely convergent, conditionally convergent, or divergent? And that's your three choices. And you may, and you will have to go through all the process of doing it. Essentially, you have to do two tests. Don't you have to find a test for the original to see if it converges or not? And then don't you have to make everybody positive and probably do a totally different test for the second time? Now, if the original diverges, I don't care. It's end of story, it diverges. You don't need to worry about making everybody positive, right? If an alternating series diverges, do you think making everybody positive is going to help? No, it just makes it even worse, right? So if it diverges, i.e. the original diverges. Stop looking, that's the answer, it diverges. Whoa, that's a lot of stuff to take in. I hope you've got your thinking cap on. Caitlin, is your brain hurting you?
It was a lot of information, but I'm doing okay.
Okay, you're, some of it was nodding stuff, some is it, oh, I forgot, but now I remember stuff.
Yeah.
Hopefully none of it was, did we do that? That's not a good sign, right?
Mhm.
Tom, how's your head feeling?
I'm just trying to remember everything.
Okay. I guess we got another 5 minutes. So what do you want to do in the 5 minutes that we have left?
Jokes.
Well, we could do that, but
I had a question. Can I ask it really
Yeah.
quick?
that's that I
uh,
prefer.
Well, okay, so if there's like a question that's like the summation as like n goes to infinity, like n equals
Uh-huh.
1 or whatever, n goes to infinity,
Yeah.
but it's of just a number like of 1,
Uh-huh.
then does that diverge because of the geometric test? Does n just equal
No.
1 and therefore?
No. It diverges. So if you went and said to me n equals 1 to infinity of, I'll pick a number 3. That diverges by the divergence test. It's almost so silly, it's hard to actually see it, but wouldn't the limit as n tends to infinity of this guy be 3? And according to the divergence test, if the limit ain't 0, it diverges.
Oh, gotcha. Okay.
And if you wanted to see what it would like, wouldn't that just be adding an infinite number of 3's together? Would you agree that would be infinitely large? It diverges.
Yeah, and that's what I was thinking. I just
You
didn't know.
might think that a half would make a difference because it's less than 1. But if you add up an infinite number of halves, don't you still get infinite?
Yeah, that makes sense. Thank you.
Right. Next question.
Can you write your conclusion with a P series, or P series is a scam?
Did you say scam as in someone's conning you kind of scam? Is that what
Like
you're
it
talking
is
about?
not like a real proof, like real
Oh, yeah,
proof.
it is actually, as long as it's a P series. So here are P series that you're allowed to say the answer. That guy converges. Why? It's a P series, P equals 3, and as long as it's bigger than 1, it converges, right? That guy is a P series. This time P is a half. A half is less than 1, it diverges. Now you are allowed a little bit of wiggle room. Isn't 10 over n cubed still considered a P series? If you want to kind of justify why you can get away with a 10, couldn't you pull it outside and just call it 10 lots of 1 over n cubed? If you stick a 2 in the bottom, it's still a P series and it still diverges. If you wanted to kind of justify that, couldn't you pull it out and say it's that guy? Well, isn't a half of infinity still infinitely big? So it ain't going to make any, it's not going to help any. So no, I don't think a P series is a con. I think it's a very simple test. But isn't the geometric series test, as long as you know what the ratio is, isn't that a pretty straightforward test as well? If R is a half, it converges. If it's 7/9, it converges. If it's minus 42, it diverges, right? Whatever it might be.
Yeah. Although when I wrote down an example on a note card a while back of when we did a limit comparison test, and it was where like we found like a related. It was like if it's n plus 1 over n to the 5th, that's basically just
1 over n to the 4.
yeah. And
Yeah.
so we said by the P series it converges, but then we
Correct.
there's like a second step of having to prove that.
Yes, the second step is the limit is an over bn equals a number. That's the limit comparison test. That's the limit part. So if you had, if I pick you up correctly, if you had a question like, prove to me what this series does. So it's not, we don't want you just to say it converges because I can tell, right? This guy would get compared to 1 over n to the 4. Are you comfortable with that? So that guy is a P series. That guy is P equals 4. That is greater than 1. So I now know what I'm trying to prove. I'm trying to prove that it converges. But I haven't proved it until I do the limit part of the limit comparison test, which means I have to find this thing. And that's going to be the limit as n tends to infinity of the original function, right, the an, divided by the comparison guy. And there I did it the long way again. If you want to save yourself a line of work in, don't I then take this guy and turn him upside down? And, you know, a few lines later, you prove the answer is 1. Now, according to the limit comparison test, we do not care the value of that. It can be 1, it can be a half, it can be 2. That's not important. What's important is it's a number. So as long as it ain't 0, or for that matter, infinity, right? Because infinity is never a number, right? As long as it's a number, you can then say, by the limit comparison test, it converges.
Okay, and if the original question had just been 1 over n to the 4th, then we could have just done the p-test and left
Yeah,
it.
if it had simply been a 10 over n to the 4 or a 1 over n to the 4, you wouldn't need to do all of this. You would go to P-series test, one-liner, boom, done. That's kind of time up, right? Now, when I see you on Monday, you're going to tell me, I hope, not tell me, you should know what time our test is and when it's going to finish. So does anybody want to volunteer that information? When is our test and when does it finish?
It starts at 5 and ends at 7. And turn
Okay.
in by 7:30.
That's the key to everything, right? It's all going to be on Canvas. Everything else will disappear. And I've been really busy today, so I haven't had enough time to put up your online test 5.